Good evening, everybody. It's hard to believe it's already session 10, and this is the third session on concrete, as Bodhi pointed out. We will talk about the shear design of beams and one-way slabs today. Okay, I would like to start with, first of all, basics, and second, a little bit of strength of materials. I think that is absolutely necessary in understanding what shear is and what it is that we do in shear design. Okay, so to start with, we are showing a beam that is made of two segments, the upper and the lower, which are glued together at this interface. If the glue is strong, then the beam bends like one beam as shown in the first picture. Okay, you wouldn't even know that the glue is there. However, if the glue is weak, then there will be slippage of the upper portion with respect to the lower portion along that interface, and the bend configuration of the beam will be as shown in the second picture. So when the beam bends like a one-piece beam, a normal beam, the glue must be applying shear stresses as shown in this picture on the upper portion, shear stresses that are trying to shorten or bring the upper portion back in, and shear stresses on the lower portion as shown by the arrows, which are trying to drag the lower portion out. Okay. Now, we can always imagine that any beam that we are dealing with is made of several horizontal layers, actually an infinite number of horizontal layers. And since a beam typically bends like this without any slippage between the layers, we must have these horizontal shear stresses acting between layers. So that's the point to the whole thing. You can intuitively see and understand the presence of these horizontal shear stresses. Okay. Then I have taken a picture from the old textbook of Strength of Materials book by Timoshenko and Young, which has been used around the world. And I would actually like to read a little bit out of my my old copy, which I looked up in preparation for this course. Okay. We begin with the simplest case of a beam of rectangular cross-section and assume that V sub x is the resultant shear force on a chosen cross-section, dividing the cross-section into infinitesimal strips parallel to the z-axis. Z-axis is this one. This is x, this is x, this is y, this is z. So these strips are parallel to the z-axis. So dividing the cross-section into infinitesimal strips parallel to the z-axis, it is reasonable to assume that on any one such strip, the shear stress tau will be uniform across the width of the beam. The shear stresses, the horizontal stresses, let us say, that we talked about, are uniform across the width of the beam. and parallel to the y-axis as shown. We also know that such shear stress on one side of the prismatic element Mn must be accompanied by equal shear stresses on each of the other three sides of the element. If we have horizontal shear on this face, there has to be horizontal shear in an opposite direction on the bottom face of the strip for force equilibrium, but those equal and opposite shear stresses will cause rotation. To have rotational equilibrium, we would need equal and opposite shear stresses that are in vertical direction on the right face and the left face. So that's what we are saying. So we also know that such shear stresses on one side of the prismatic element Mn must be accompanied by equal shear stresses on each of the other three sides of the element. Thus, we must observe at the outset that there will be horizontal shear stresses between layers of the beam parallel to the neutral plane, as well as transverse shear stresses between cross sections, and that at any point in the beam, these complementary shear stresses are equal in magnitude. So this is extremely important. I will read again. Thus, we must observe at the outset that there will be horizontal shear stresses between layers of the beam parallel to the neutral plane, as well as transverse shear stresses between cross sections, and that at any point in the beam, these complementary shear stresses are equal in magnitude. This at once leads us to conclude that the shear stress tau must vary as we go from the top to the bottom of the beam. So the writing points out that at the top, the shear stress must disappear, must be zero. At the bottom, the shear stress must be zero. So in between, if there are shear stresses, then there must be variation in those shear stresses from the top to the bottom. Okay. Now we are looking, so the key to the true law of variation of tau with y comes from examining the equilibrium of an elemental block, Pn, P1, N1, this block, okay, which we have taken out of the beam, Pn, P1, N1, between two adjacent cross sections Mn and M1, N1, distance dx apart. The distance between this section and that sections is dx. Okay, let me, okay, I don't want to read anymore. So you understand that we have taken this element outside of the beam on the left. So at this section, Mn, the bending moment is M. At this section, M1, N1, the bending moment is D plus Dm. The bending moment has changed a little bit. Okay. The stresses due to bending are sigma. On the left face, it is sigma. On the right face, where the moment is D plus Dm, it is sigma plus D sigma. The stress has increased a little bit. Okay. And the horizontal stresses are kept in equilibrium by the shear stress, horizontal shear stress acting on the top of the element. Okay. So that is our picture. This is the, this picture is not the same as that. On the next picture, we are drawing the section Mn. Okay, so we are drawing this section. At a depth y from the neutral axis, sigma dA, this is an elemental area, sigma dA is Sigma, the bending stress, is M over I times Y. You need to know that from basic strength of materials. So sigma dA is My over I times dA. So sum of the normal forces over Pn over this entire area would be from integration from Y1 to C1 is the distance to the end. C1 was shown in the previous picture. So this is C1 from neutral axis to the bottom. That is C2 from neutral axis to the top. So the sum of the normal forces over Pn, this hatched portion, is integration from Y1 to C1 of My over I dA, this expression. Now we go to the other section, M1, N1, where the bending moment has increased a little bit to M plus dm. The sigma dA is now M plus dm over I times Y dA, so that sum of normal forces over Pn is the integration from Y1 to C1 of this larger moment M plus dm by I times Y dA. Okay? So for equilibrium of this elemental block, the horizontal force tau works over the distance dx, and the width of the beam is b. So the total shear is tau b dx is equal to the force on this face minus, no, the horizontal force which is to the left is the total normal force on this face, which is this integral, minus the total normal force on the left face, which is this integral. And when you take this away from that, you end up with this dm over I times y integrated from y1 to c1. So this is what we get from force equilibrium of that elemental block. That tells you that the tau is dm dx, then 1 over ib. Okay, I is here, b comes from the other side, and then the integral y1 to c1 of y dA. Okay, we have taken dm out. Dm does not vary with height. So tau is dm dx 1 over ib times this integral. Dm dx is actually shear. Shear is the first differential of the moment. I do not know that. We need to get back to that. This again is basic strength of materials. So we get V over, so tau is equal to V over IB times this integral, y1 to c1, y dA. This integral is denoted by Q, and that gives us the very familiar expression, tau is equal to VQ over IB. Tau is the shear stress at a distance from the neutral axis. Okay, in this case, the distance is y1. So we wrote the same expression again. Q is integral of y dA. Y is the distance of this elemental area from the neutral axis. Okay, dA is the elemental area. We integrate that over the hatched portion of the section from y1 to c1 is the distance to the bottom. So dA is the width b times dy. the incremental depth of the elemental area. Okay. So we can take the B out of the integral. That doesn't vary with depth. Integral y dy from y1 to h2. So y integral of y is y squared by 2. We take it from the limits of y1 to h2, and that gives us this. So the q that we are looking for in our particular case is b by 2 times h squared by 4 minus y1 squared. Okay. So tau is given by this expression. So at the top and the bottom of the beam, where y1 is plus h over 2 or minus h over 2, tau disappears as it should. Okay. So when y1 is h over 2 plus or minus, doesn't make any difference, tau comes out to 0. So at the top and the bottom of the beam, there is no horizontal shear stress, as we all know. At the neutral axis, where y1 is equal to 0, tau is given by this expression, and it comes out to, so tau at the neutral axis is b over 2, I is bh cubed by 12, and h squared by 4, y1 is 0. Are you with me? So b over 2 remains. I is bh cubed by 12. We have written it out. H squared by 4, y1 is 0. So at the neutral axis, tau is 3 over 2. 12 over 8 is 3 over 2. V over BH. V over BH is average shear stress over the entire section. So the maximum shear at the neutral axis is 1.5 times the average shear. So quite a few important conclusions. The horizontal shear at any level is BQ over IB, the expression that we all know. We kind of derived it from first principles. At the top and the bottom of the beam, shear stress is 0. At the neutral axis, the shear stress is the maximum, and it is equal to 1.5 times the average shear stress. Okay? So this is kind of the overall picture. The total depth of the beam is h. At the section that we are looking at, the shear is V. The average shear stress over the section is B over BH. This shear is horizontal as well as vertical, as you know. And then at the neutral axis, the maximum shear is 1.5 times V over BH, the average shear. Okay? So those are very basic things that we need to keep in mind in shear design. This has to be kind of second nature, the calculation of the horizontal shear stress using BQ over IB, fully understanding what the quantity Q is and the variation of the shear stress along the depth of the beam. Okay. Then the principal stresses, which are easily established using the Morse circle. This is the second topic from strength of materials that I will take you through, and then we will go into ACI 380 and BNBC shear design, which is our topic today, which is where we are headed. But these preliminaries, I think, are extremely important. So if we take this element as in the previous picture, pretty much, okay, a beam under transverse loading, in this case, it's loading in the middle, simply supported at the two ends. we take an element, in this case, below the neutral axis. So that element will be subject to normal stresses denoted by those arrows, the sigma x. The element is subject to normal stresses in the y direction, that is sigma y. There are shear stresses on the left and right face, that's tau xy, and there are also shear stresses on the upper and the lower face, which are also tau xy. The shear stresses are the same. So the applied stresses, if we may call them that, the stresses caused by the applied load are sigma x in the x direction, sigma y in the y direction. The x direction is indicated clearly, the y direction is indicated clearly, and tau xy. Okay. Now, so on, if you pick any element at random, this is what you have. You have bending stresses and shear stresses. However, if you take an element inclined at a particular angle, then it is possible for the shear stresses to disappear and for the element to be subject only to bending stresses. And those bending stresses are called principal stresses. Those are the largest stresses that an element can be subject to. Okay? This concept of principal stresses, I'm sure, is not new to you. I'm trying to very, very briefly trying to bring it back. The idea is, when we talk about principal stresses, there are no shear stresses associated with them. Okay? And they are the largest stresses, that largest meaning largest or the smallest stresses that an element is going to experience. Now, in order to figure out the sigma 1 and sigma 2, the principal stresses, we typically go to this construction of Morse circle, and these are the steps, and let us implement them rather than read them. Okay, so this is our element. We have on the let us say right and the left face, the vertical faces, sigma x and tau xy. Okay, so we plot along the x-axis sigma x, that brings us to point F, and we plot tau xy going up. Let us say this tau on the left and right face is a positive shear, okay, causing clockwise moment. Then we plot sigma sub y, that brings us to point F1, and on the top face and the bottom face there are shear stresses that cause counterclockwise moment. So this is a negative tau xy, and we plot that. That brings us to point D1. So the stresses on the right and left face took us to point D. The stresses on the upper and the lower face take us to D1. Now we draw a circle with DD1 as the diameter. Okay, so we go to the center of D and D1. That's the center of our circle. This is the radius. This is the radius from C to D, and this is our Morse circle. Okay, now the principal stress sigma 1 is shown here. Sigma 1 is let's go to the next page. So sigma average is the distance from O to C. Remember again, sigma x takes us to F, sigma y takes us to F1. The average of sigma x and sigma y will take us to the point C, and the distance OC is sigma x plus sigma y by 2, the average of the two. It just from the figure. Okay? The radius R is this distance CF is sigma x minus sigma y. Sigma x minus sigma y is the distance FF1 divided by 2. So this is sigma x minus sigma y divided by 2, and the vertical distance, and the vertical distance is tau xy. So the radius is square root of this distance squared and that distance squared, which is equal to this. And this angle, the tan of this angle is as shown here. Okay, tan of 2 phi a is, okay, if the I should have pointed out, if the principal stress is inclined at phi a, then on the Morse circle that angle will be 2 times phi a. So anyway, I don't know that we will do a lot with the angle, but the sigma average is sigma sub x plus sigma sub y by 2. The radius is equal to that. So now the principal stress sigma 1, which is from here to there, okay, is OC plus CA. OC is sigma average and CA is the radius of the circle, which is equal to that. Okay. So the first principal stress sigma 1 is given by this expression. The second principal stress sigma 2, which is the distance O to B, is sigma average, the distance O to C, minus the distance CB, which is the radius, and that is then given by this expression. So if we know sigma x, sigma y, tau xy, then we are in a position to figure out the principal stresses sigma 1 and sigma 2, which are not associated with any shear. Those are normal stresses, either tension or compression. Okay, so now we are back to a beam under uniform load, simply supported. We have taken an element 1 at the neutral axis. We have taken an element 2 that is basically at the bottom of the beam. On element 1, sigma x and sigma y are equal to 0 because it is at the neutral axis. Okay, so if sigma x and sigma y are 0, then sigma 1 and sigma 2, by the expressions we derived, this expression, okay, so if sigma x is 0, sigma y is 0, then sigma 1 is simply tau xy, and sigma 2 is also tau xy. Okay? The directions are different. This is plus tau xy, this is minus tau xy. And that's what we have written here. Sigma 1 is negative sigma 2 is equal to tau xy. And if you want the inclination of that shear stress, 2 phi a comes out to 90 degrees and phi a comes out to 45 degrees. On element 2, which is at the bottom, the sigma y is 0. Okay, at the bottom there is no normal stress acting down. So sigma 1 comes out to this, sigma 2 comes out to this, and the angle comes out to this. Okay? So this is the difference between element 1 and element 2. We are definitely in a position to plot the sigma 1 and sigma 2 along the span of the beam. Okay, element 1, element 2, same beam. On element 1, we have only shear stresses, no bending stresses. That gives us principal stresses as shown in the picture. Okay, on those inclined faces, we have tension equal to the shear. On those inclined faces, we have compression also equal to the shear. On this element, we have bending stresses and shear stresses that will give us principal stresses as shown in the second picture, inclined at some angle, okay, not 45 degrees, some angle lower than 45 degrees. Now, if we plot sigma 1 along the length of the beam, we will get the lines that are solid lines in the picture. And if we plot sigma sub 2, the compression stresses along the length of the beam, we will get the dotted lines. So we have plotted trajectories of tension stresses in solid lines, and we have plotted trajectories of compressive stresses by the dotted lines. For any beam, we are in a position to do this. Not that we typically do this, but this is very, very important from shear design point of view, because the central point why I went through so much strength of materials is that, remember, the very first thing, one of the first things I told you is concrete is reasonably strong in compression, but concrete is weak in tension. It cannot carry much tension. And we are seeing significant tensile stresses as indicated by the solid lines. Okay, these tensile stresses quite often, actually, unless you are here someplace, these stresses are inclined. These are inclined tensile stresses, not parallel to the neutral axis as we typically visualize. And these inclined tensile stresses will cause cracks perpendicular to the tension. So unless we have reinforcement trying to minimize those cracks or contain those cracks, we will be in trouble. Okay? So when we talk about shear design, we are designing against this diagonal tension. That's precisely what we are doing. Okay, we are trying to prevent the diagonal tension from destroying our beam. The inclined cracks that will result from the diagonal tensile stresses must be contained by providing suitable reinforcement. So that's what shear design of concrete beams is all about. I want you to understand it. I want you to retain it for all time to come, and that will stand you in good stead. In direct shear, concrete is pretty strong, and it is very, very seldom. There are applications where we design concrete against direct shear, but those are very rare. So when we talk about shear design, we are talking about design against resistance to diagonal tension. So In summary, resisting shear in concrete is resisting diagonal tension in concrete. Diagonal tension is maximum at the neutral axis of a given section and zero at the top and the bottom edges of the section, as we saw. Okay, the shear stress is maximum at the neutral axis, so is diagonal tension. Shear stresses disappear at the top and the bottom, so do diagonal tension. So resisting shear in concrete is resisting diagonal tension in concrete. Diagonal tension is maximum at the neutral axis of a given section and zero at the top and bottom edges of a section. Okay, now a few things that are good to kind of appreciate. Yeah. So typically the ratio V is the shear, M is the corresponding moment at the section, D is the effective depth. Okay. V D over M is a how do you call it? It's a unitless number, non-dimensional quantity. Okay, VD over M. And VD over M tells you about how a beam is going to behave. At least there are some indications as to how it will behave if you look at the VD over M ratio. Now, in a beam as shown in the picture, simply supported, this is the bending moment diagram, this is the shear diagram. At this location, the shear is large, the bending is large. Both the moment and the shear are large. At this section, we have large shear, very small bending. Okay? So it tells you about what kind of a ratio, BD over M, we are looking at as we go along the beam. Uniformly distributed loading, the same beam. This is the bending moment diagram. This is the shear diagram. Here, as before, the moment is large, the shear is low. Here, the moment is small, the shear is large. Okay, so as we go from the center to the supports, that is what changes. Okay. This is a beam continuous over the middle support. At this location, we have large moment, no shear or very small shear. At this location at the support, both the moment and the shear are high. Near at this inflection point or whatever you want to call it, the moment has become very small to zero, but the shear is still large. And at this location, the shear is large, the moment is small. Okay. Now, we are looking at a reinforced concrete beam without shear reinforcement. Okay, so this is reinforced concrete beam on this is the left support. There is a support to the right someplace. This is the tension reinforcement. The important thing is that there is no shear reinforcement. Okay, we talked about the principal tensile stresses. Those principal tensile stresses are the largest at the neutral axis. So diagonal tension stress near neutral axis, that's the largest diagonal tension. When that equals and then exceeds the tension strength of the concrete, there will be cracking at the location of the neutral axis. Okay. And this kind of cracking is called web shear cracking. This is now coming home. Okay, this is now hardcore shear design of concrete beams. There is web shear cracking and flexure shear cracking that we deal with all the time. Okay. So what is web shear cracking? When the principal tensile stresses, which are the largest at the neutral axis, equal or exceed the tensile strength of the concrete. That tensile strength, it has been established by many tests, experimental tests, is between 1/4 and 40% of square root of f sub c prime in SI metric units. Okay, 0.25 to 0.4 square root of f sub c prime. We take it as 0.29 square root of f sub c prime. So the shear at cracking V sub CR, shear corresponding to this flexure, corresponding to this wave shear cracking, that's what we are calling V sub CR. V sub, okay, the stress at flexure shear cracking is lowercase v sub CR. That is uppercase V sub CR, the force that causes wave shear cracking, the shear force that causes wave shear cracking, divided by BD. B is the width of the beam, D is the effective depth. So that is, we take it equal to 29% of square root of f sub c prime. This is between 25 and 40. We are taking it 29%. So the expression for web shear cracking stress is 29% of square root of f sub c prime. This web shear cracking, which starts at the neutral axis location, is it does happen, but it's relatively rare. Okay? What is much more common is flexural cracks open up. We know why. We have flexural tension, and at the bottom the flexural tension is horizontal. At like in the middle of the beam, the flexural tension is horizontal. We saw that from the principal stress trajectories. So the flexural cracks are vertical or near vertical, okay, as we go towards the supports. So here they're vertical. As we go near the supports, they get inclined. Here they're more inclined. Anyhow, so shear stress at the tip of a flexure shear crack is because of the crack, the shear stress at the tip of the crack can be quite high. So shear stress at the tip of the crack can be much larger than what the shear that we would have had there in the absence of the crack. Simultaneous bending stress increases the diagonal tension. Okay, at that location, at the tip of the flexural crack, we not only have shear but also have normal stresses, and the two together gives us diagonal tension stresses that are significantly higher than the V over BD. Now, so flexure shear cracking happens at a significantly lower stress than the 0.9 square root of f sub c prime value that I showed you on the previous slide. It tends to happen around half of that. We take it as 0.16 square root of f sub c prime. So web shear cracking stress is 0.29 square root of f sub c prime. Flexure shear cracking stress, on the other hand, is 0.16 square root of f sub c prime. It is much liable. Everything depends on the proportions of the beam. If it is a thin-webbed beam and all kinds of things, but the flexure shear cracking happens at a lower stress than web shear cracking, and this is why flexure shear cracking is much more common than web shear cracking. Now, the flexural reinforcement, we remember we are talking about beams without shear reinforcement, but there is flexural reinforcement, and that flexural reinforcement plays an important role. Large tension reinforcement percentage rho results in smaller and narrower flexural tension cracks prior to formation of diagonal tension cracking. That is common sense, right? Large tension reinforcement percentage results in smaller and narrower flexural tension cracks prior to formation of diagonal tension cracking. This leaves large area of uncracked concrete to resist shear. So the cracking shear stress, which would be if we don't consider this effect, which would be 0.16 square root of f sub c prime, goes up by this expression. This is everything I'm showing, that number is experimentally derived based on a lot of testing. Okay? So the cracking strength, this is flexure shear cracking strength, is the concrete contribution 0.16 square root of f sub c prime plus the contribution of the longitudinal steel, the steel that is there for bending. Okay? And so it is given by that expression, and the two together must be no higher than the web shear cracking strength of 0.29 square root of f sub c prime. The web shear cracking strength, for obvious reasons, is not helped by the longitudinal reinforcement that is at the neutral axis. It has nothing to do with the longitudinal reinforcement. So, simplified expression for web shear, not web shear, for flexure shear cracking strength. So this is 0.16, we take it as 0.17 and forget about rho. That is just a simplification. You don't have to do this, but that is done fairly often. Okay, so shear and diagonal tension, reinforced concrete beams without shear reinforcement, behavior of diagonally cracked beam. So we are talking about diagonal cracking for reasons that I have gone through. Once a diagonal crack forms, two things can happen. It goes all the way through, causing failure of the beam. That would be diagonal tension failure. That is not uncommon by any means. Or the diagonal crack may stabilize and the beam could go on carrying higher loads. Both scenarios are possible. Okay? So let us look at how a diagonal crack, once it opens up, may stabilize. So behavior of diagonally cracked beam. This is the diagonal crack, obviously, that has formed. Okay, the external shear has to be, the external shear is equal to this reaction R1 minus this load P1. Okay, we are talking about this portion of the beam, the crack to the left. So the external shear is R sub 1 minus P sub 1. The external shear has to be equal to the internal shear. Internal shear is the shear in the uncracked portion of the beam, that is V sub C, the concrete in compression. Then the shear that is resisted by dowel action of the reinforcement. I hope you understand dowel action is like kinking. And the aggregate interlock shear. V sub I is the shear that is resisted by aggregate interlock because the surfaces of the crack are rough and the aggregate, the stone on that surface, rub against one another. So the vertical component of the aggregate interlock shear is V sub I y. So external shear is equal to internal shear. Internal shear is the shear in the concrete in compression V sub C plus the shear that is carried by double action plus the vertical component of the aggregate interlock shear. So V sub C, the shear in the compression concrete, is the external shear minus the shear that is carried in double action minus the vertical component of the aggregate interlock shear. Yeah. Now, external moment is this R1 multiplied by the distance XA. Okay, so we are taking moments about the point A. External moment is R1 times XA minus P sub 1 times XA minus X1. If you look at the picture, everything should be very clear. So external moment is R1 times XA minus P1 times XA minus X1. Internal moment about point A would be the tensile steel force at section B, that is TSB, times the distance Z, you can call it the lever arm, okay, plus the dowel shear V sub D at B multiplied by this distance X, okay, from the dowel force to the point A, and the dowel shear is typically not big, so that term can be neglected. Then we have internal moment equal to the tension at point B multiplied by the Z. Okay. So if we write M internal is equal to M external, then the tension at point B is M external at point A divided by Z. That is an interesting conclusion and observation. So tension at B is equal to the moment at A divided by the lever arm Z. It is not the moment at B. That's what the diagonal crack has done. Okay, so we did derive a fairly significant conclusion. So formation of diagonal cracks produces the following redistribution of forces and stresses. Shear stress on concrete increases from V external over BD to VC over BY. Okay, so before the diagonal crack, the shear was V external and the stress was that divided by the section BD. But after the cracking, the shear is the shear in the concrete, and the area of the uncracked concrete is B times Y. Okay, I don't know if I pointed out the Y distance here. Okay, so shear stress on concrete increases from flexural compression C sub C acts over BY, the uncracked concrete section, rather than B times KD, which it would normally do before the diagonal crack opens up. And tension in steel at B is caused by bending moment at A. These are all quite important. Shear stress on concrete increases from B external over BD to B sub C over BY. Flexural compression acts over BY rather than B times KD. and tension in steel at B is caused by bending moment at A. If both materials can resist the increased stresses, equilibrium re-establishes itself. So the opening of a diagonal crack does not have to be the end of the beam. That is the message. Okay. Now we come to shear and diagonal tension reinforced concrete beams with shear reinforcement. Okay. That is the shear reinforcement, as you see in the picture. The same diagonal crack, same uncracked concrete section. This is the aggregate interlock force. This is the shear carried by dowel action and so forth. So shear resistance mechanism consists of V sub C, shear resisted by the concrete as before. V sub S, shear resisted by the stirrups, that is new. V sub D, shear resisted by dowel action of flexural reinforcement. And V sub IY, shear resisted by aggregate interlocking along inclined crack. Now V external is V sub C, the shear carried by the resisted by the uncracked concrete, plus V sub S, shear resisted by the vertical shear reinforcement, shear resisted by dowel action, V sub Y, the vertical component of the aggregate interlock shear. Okay. The shear resisted by the vertical shear reinforcement is, if we take one of those stirrups, total cross-sectional area A sub B, if there are two legs, that will be the area of the two legs. So A sub B multiplied by F sub YT, the yield strength of the reinforcement in this stirrup. Okay. And we will sum over however many stirrups are crossed by that crack. So we will take the force, the tension in each stirrup, which will be A sub B F sub YT, and will multiply by the number of stirrups that are crossed by the diagonal crack. And that number we are taking equal to X, the horizontal extent of the diagonal crack, divided by the spacing of the stirrups, X over S. So the difference between this and the next one, so here V sub C plus V sub S plus V sub D plus V sub IY is the external shear. V sub C we have left alone, V sub D we have left alone, V sub IY. Okay, so the three components together, the three components of shear resistance, the only thing we left out are the stirrups. We are calling that the cracking shear strength of the concrete, V sub CR. Okay. The shear that is resisted by the compression concrete, that is intact, shear that is resisted by dowel action, and the shear that is resisted by aggregate interlock. All together, we are calling that the cracking shear, V sub CR. And we are assuming that this X, the horizontal extent of the crack, is equal to the effective depth. At failure, the external shear is the nominal shear strength. Okay, that's what nominal strength means. At that shear, we have shear failure. So the nominal shear strength then is the cracking shear strength of the concrete V sub CR plus A sub B F sub YT, the shear resisted by an individual stirrup, multiplied by the number of stirrups caused by the crack, which should be D over S instead of X over S, because we have assumed X is equal to D. So nominal ultimate shear stress, if we want nominal ultimate shear stress rather than strength, then we divide by BD, and that will be a lowercase v sub CR, capital V sub CR divided by BD, and A sub B F sub YT divided by BS. This is just division by BD. So this is the important part. The nominal shear strength is the cracking strength of the concrete, diagonal cracking strength of the concrete in shear, and the shear that is resisted by the vertical shear reinforcement. Okay. Now we are showing the contribution of the various components to shear resistance. This is shear resisted by the compression concrete, shear resisted in double action, shear resisted by aggregate interlock, and this is shear resisted by the stirrups. Until inclined cracks open up, the stirrups don't do anything. Okay, they have to be in a way activated. They have to be crossed by diagonal cracks. But once diagonal cracking starts, incline cracking starts, the stirrups go on carrying increasing amounts of shear. Okay. The contributions of the other components are more or less constant. The contribution of the vertical shear reinforcement goes on increasing, okay, as the loads on the beam increase. Okay. So you can see the relative proportions of shear in the compression concrete, shear carried by double action, shear carried by aggregate interlock, and how they remain the same or change a little as the beam is loaded more and more. Once the stirrups yield, then obviously their contribution levels off. That point we are looking at wide cracks, and so this aggregate interlock shear as well as the dowel shear, those drop off. Okay. So this is a very, very important picture if you are going to understand the whole mechanism of shear resistance and where the resistance comes from. Okay. Now, from this point onwards, it's SEI 318 BNBC. As before, 31808 section numbers are black, and BNBC 2020 section numbers are in blue. So this is mostly coded language, unless I tell you. Okay, so for non-priestess members, sections located less than a distance d from face of support shall be permitted to be designed for P sub u computed at a distance d. This is very important. We call it the critical section for shear design. So you do not typically have to design a beam for shear for the shear at the support face. We typically design a beam for shear or diagonal tension, as I have pointed out, for shear at a distance d from the support face. So the critical section for shear is located at a distance d from the support face, d being the effective depth. Now, what I said is true provided a number of conditions are met, and those conditions we will look at next. But this fact, again, the fact that we take the critical section 1D away from the support face is again because we are designing for diagonal tension. It is not designing directly against shear. So what I just said, the critical section at a distance d from the support face is applicable if all of the following conditions are satisfied. Support reaction in direction of applied shear induces compression into the end region of the member. Okay, the support induces compression rather than tension. Okay, that would typically be the case. The support reaction in direction of applied shear introduces compression. In a typical beam, that's what happens. Okay, the beam wants to go down, if you like. The support keeps it from going down and produces compression. Loads are applied at or near the top of the member. This is important. If you have a beam with ledges, like precast spandrel beams, and you apply the loading on the ledge rather than on the top of the beam, then you do not satisfy this condition. Loads are applied at or near the top of the member. No concentrated load occurs between face of support and location of critical section. This is extremely important. You cannot take the critical section 1D away from the support face if within the distance D we have a concentrate, one or more concentrated loads sitting on the beam. Okay, so no concentrated load occurs between face of support and location of critical section. Okay, these are some illustrations. The top picture is what I was describing. So this is a precast beam with a ledge. The loading is applied on the ledge, not on the top of the beam. The critical section goes back to the support face. It is not 1D away from the support face. So here, there is no compression at the support. The support, this beam is hanging from something, so the support does not provide compression, and then the critical section is at the support face. Okay? This is a normal situation. This is a beam. The loading is at the top, not shown. The critical section and the support provides compression, and the critical section is 1D away from the support face. Same thing here. Okay, it's a beam column joint. There is compression at the support. The loading is at the top. The critical section is 1D away from the support face. Here, a concentrated load sits close to the support, so the critical section is at the support face, not at 1D away from the support face. Okay. Now, design for shear. This is as we discussed at the first concrete session. In all strength design, the design strength must be larger than or equal to the required strength. Required strength is V sub U. That has to be calculated from the applied loads by structural analysis. And V sub N is the nominal shear strength. We reduce it by a strength reduction factor phi to get to a design strength. In shear design of ACI 318 and BNBC 2020, phi for shear is 0.75. There are exceptions to that, which we may come across as I take you through other stuff, but normally, unless something specific is said, phi is 0.75. Okay. Now the nominal shear, so required shear strength V sub U has to be larger than or equal, has to be smaller than or equal to the design shear strength phi times V sub N. Required shear strength has to do with structural analysis, applied load and the structure. V sub N is something we will calculate from the given section. Phi is specified to be 0.75. V sub n, nominal shear strength, where does it come from? Part of it is contributed by the concrete, V sub c, and part by the shear reinforcement, V sub s. This V sub c is what we were calling V sub cr previously when we were talking about mechanisms. Okay, this is not just the shear in the compression concrete, just so that you understand. There is a little bit of a switch in notation. Okay. So V sub n is contributed partly by concrete, partly by the shear reinforcement. And the concrete contribution may have those other multiple parts, may have double shear in it, may have aggregate interlock shear in it. That's totally fine. V sub c is shear strength provided by concrete, calculated in accordance with section such and such. V sub s is shear strength provided by reinforcement, and we will look at the calculation. Okay. In determining V sub n, the effect of any openings in members shall be considered. Okay. This is an important statement, but going into that will be time consuming. So I have confined myself to giving you 4 references, all of which are quite good in telling you how you may approach that problem of openings in your member when you are calculating shear strength. And I will leave it at that. In determining V sub c, the concrete contribution to shear strength, whenever applicable, effects of axial tension due to creep and shrinkage in restrained members shall be considered. That will take away from shear strength. Any tension takes away. And effects of incline flexural compression in the effects of incline flexural compression in variable depth members shall be permitted to be included. Any compression will improve V sub c, and we are saying that if there is actual compression, as there will be in inclined members, that shall be permitted to be included. You don't have to include it, but you are allowed to include it. In the case of tension, you have to consider it. It takes away from V sub c. Now, something that basically a twist, if you like. So the value of square root of f sub c prime, whenever we talk about V sub c, we typically express it in so many square root of f sub c prime, and that is sometimes true of V sub u also. The square root of, so let us say shear strength is so many square root of f sub c prime. Square root of f sub c prime shall not exceed 8.3 megapascals, except as allowed in 11.121. So in American units, square root of f sub c prime cannot be taken any more than 100 psi. The background to this is we do not have test results for beams having, or didn't have, having compressive strength in excess of 10,000 psi. For f sub c prime exceeding 10,000 psi, we did not have shear strength test results. So ACI 318 in several editions ago said, let us restrict concrete strength to 10,000 psi, which means square root of f sub c prime shall be restricted to 100 psi. That's what you are looking at here. 8.3 MPa, square root of f sub c prime. Okay. Now, we did not mean to say concrete strength cannot exceed 10,000 psi. What we meant to say is if you have 15,000 psi concrete For shear strength calculation, you will count on 10,000 psi. You will ignore the other 5,000 psi. But then we went on to say, if you want to take advantage of the shear contribution of the additional 5,000 psi of concrete strength, you will have to provide more than minimum shear reinforcement. Okay? If you do, then you can take full credit. How much more shear reinforcement, that will be coming up on subsequent slides. Okay, so here you are looking at the very first part of the picture. Square root of f sub c prime shall not exceed 100 psi, meaning concrete strength shall be restricted to 10,000 psi. Okay, unless except as allowed in. So there are exceptions to that. So this is the background that I probably already gave you. Because of a lack of test data and practical experience, with concretes having compressive strengths greater than 70 MPa, that would be 10,000 psi, the 1989 edition of the code imposed a maximum value of 8.3 MPa on square root of f sub c prime for use in the calculation of shear strength of concrete beams, joists, and slabs. Exceptions to this limit were permitted. Now, values of square root of f sub c prime greater than 8.3 MPa shall be permitted in computing V sub c for reinforced concrete beams and concrete joist construction, having minimum web reinforcement in accordance with 11463. So if you want to take advantage of the shear contribution of additional concrete strength in excess of 10,000 psi, you will have to provide web reinforcement in accordance with 11463. Okay. Before we go there, this is, okay. So based on the test results, an increase in the minimum amount of transverse reinforcement is required for high strength concrete. Based on test results, an increase in the minimum amount of transverse reinforcement is required for high strength concrete. In ACI 31889 through 99, increase in minimum amount of shear reinforcement was sudden. 31802, increase became gradual. Okay, let me go there. I'll come back. I have a figure. Oh, what happened to that? Second. I know that I have the figure. Give me 1 second. Strange. Yeah, this is what I'm looking for. So because of the, yeah, anyway, so in where we started is this 70 MPa is 10,000 psi. So this is the shear reinforcement. We provided minimum, we provided, or we had to provide minimum shear reinforcement anyway. When the concrete compressive strength exceeded 10,000 psi, if it were 10,001 psi, and we wanted to benefit from the shear contribution of the extra 1 psi compressive strength, we had to provide 2 times the minimum shear reinforcement. Okay, we had to apply a multiplier of 2 to the minimum shear reinforcement. that multiplier of 2 went up to 3, corresponding to 15,000 psi compressive strength. And after 15,000, we did not increase the multiplier anymore. So all of a sudden at 10,000 psi, we had to provide twice the minimum shear reinforcement that we would otherwise provide. That 2 times minimum went up to 3 times minimum for 15,000 psi, and then it remained level. 31802, we abandoned that those abrupt changes, and we provided minimum shear reinforcement that varies with compressive strength of the concrete. Okay, so that's what we were. Yeah. Anyway, so let me go back where I was. Should have marked the. Okay, so based on test results, an increase in the minimum amount of transverse reinforcement is required for high strength concrete. So 31889 through 99, increase in minimum amount of shear reinforcement was sudden. 31802, increase became gradual, and it will come back as you saw. Okay. Now V sub C shall be computed by provisions of section such and such unless a more detailed calculation is made in accordance with another section. So V sub C shall be computed by a set of provisions unless a more detailed calculation is made in accordance with another section. Throughout this chapter, except in 11.6, which is shear friction, which we will not discuss today, lambda shall be as defined in section 861. Lambda lightweight concrete factor is in chapter 8, and you can look that up. I didn't reproduce that. Okay, so this is how to calculate V sub C, the concrete contribution. Okay. There is the regular calculation, and then there is detailed calculation. As you saw, you can do it 2 ways, and this is the usual way of calculating V sub C. For members subject to shear and flexure only, as opposed to axial force, V sub C is 0.17, the lightweight concrete factor square root of F sub C prime B sub WD. We have seen this 0.17 square root of F sub C prime for quite a while now. Okay. So that was flexure and shear only, no axial force. For members subject to axial compression, this term is added. N sub U divided by A sub G. N sub U is the compression, factored compression. A sub G is the gross cross-sectional area. And this, if you want this expression, then the N sub U over A sub G has to be in MPa. So the first equation is shear and flexure only. This is axial compression. Look at this. So in this simplified calculation or regular calculation, for members subject to significant axial tension, V sub C shall be taken as 0 unless a more detailed analysis is made using section such and such. V sub C, now comes the more complicated calculation. V sub C shall be permitted to be calculated by the more detailed calculation 221 through 223, more detailed calculation. This I'll skip. I'll let you read. I don't have a lot of, this can be used. Anyway, I don't want to spend time on the detailed expressions. I think they are understandable if you read them. Here, when you have significant axial tension, instead of taking V sub C is 0, there is an expression, so you can get something out of the concrete. So that is regular calculation, there is detailed calculation of V sub C. That detailed I skipped to save a little bit of time. For circular members, effective shear area, this is important. If you have, well, how common it is to have circular beams, I don't know. But anyway, for circular members, effective shear area is taken as the product of the diameter and the effective depth of the concrete section. So diameter and effective depth. Effective depth D can be taken as 80% of the diameter of the section. This is kind of interesting. So diameter times 80% of the diameter. That would be your effective section. Types of shear reinforcement. Here again, there is a lot of stuff that I will skip because most of it is old to antiquated. I don't know, bent bars and so forth. You know, I haven't seen those in those are so labor intensive. I do not know, maybe in Bangladesh there is some limited usage, but I doubt it. So the following are permitted as shear reinforcement. Stirrups perpendicular to axis of member, by far the most common. Welded wire reinforcement, what we used to call welded wire fabric, with wires located perpendicular to axis of member. Okay. Welded wire reinforcement with wires located perpendicular to axis of member. I do not know if this usage is common in Bangladesh. Here it is not uncommon. The advantage is, you know, the how should I say, instead individual stirrups, you know, some of the work is already done when you get fabric on the job. So anyway, stirrups perpendicular to axis of member, welded wire reinforcement with wires located perpendicular to axis of member, spirals, circular ties or hoops, those are not uncommon at all. And then the following are permitted as shear reinforcement. Stirrups making an angle of 45 degrees or more with longitudinal tension reinforcement. Longitudinal reinforcement with bent portion making an angle of 30 degrees or more with the longitudinal tension reinforcement. Combinations of stirrups and bent longitudinal reinforcement. Yeah, some of this stuff I don't want to spend time discussing. Okay, this is extremely important. So F sub YT, the yield strength of shear reinforcement is limited to 420 MPa. Please keep that in mind. Okay, limited to. If you use higher strength reinforcement in shear calculations, you cannot use F sub YT in excess of 420 MPa. If it is welded deformed wire reinforcement, then yield strength is restricted to 550 MPa. These are the various types of shear reinforcement: stirrups, welded wire fabric, inclined stirrups, as it says, more than 45-degree angle. So those are the inclined stirrups. Longitudinal bent bars, this is the tension bar bent up and then it becomes a compression bar. This used to be done long time ago. Combination of bent bars and stirrups, and then the spirals. Okay, so this is very common. Sorry, this is not uncommon. That is not terribly uncommon, but these inclined things I think are not common. Stirrups and other bars or wires used as shear reinforcement shall extend to a distance d from extreme compression fiber and shall be developed at both ends. Okay, so this is not unimportant. Stirrups and other bars used as shear reinforcement shall extend to a distance d from extreme compression fiber and shall be developed. We will talk about development of web reinforcement tomorrow. It is important that the stirrups be developed. Minimum shear reinforcement. So after diagonal shear cracks are formed, additional deformation results in the growth of shear cracks, and it is resisted by shear reinforcement. This is very, very important to to get in your heart even. Okay, so this is how it always is. So after diagonal shear cracks are formed, additional deformation results in, additional deformation will be if you keep on loading your beam, results in the growth of shear cracks, and it is resisted by shear reinforcement. Prior to 31808, minimum amount of transverse reinforcement was not a function of concrete compressive strength, as you saw. Anyway, minimum shear reinforcement is given by this expression. I said is given by, used to be given by. Okay, so ACI 31899, we are talking about 31808, remember, in BNBC 2020. So this is in the past. But as we said, prior to 31802, minimum reinforcement, minimum shear reinforcement did not depend on compressive strength. This was the expression. Experimental tests verified that the required amount of shear reinforcement should be increased with higher concrete strength to prevent sudden failure after inclined cracks were formed. This is extremely important. I will read it again. Maybe this is the fifth time, doesn't matter. Experimental results verified that the required amount of shear reinforcement should be increased with higher concrete strength to prevent sudden failure after the inclined cracks are formed. So it is more reasonable that concrete compressive strength is included as a parameter in determination of minimum amount of shear reinforcement. So this is now the expression. It has square root of f sub c prime in it. This is a sub v minimum. Something close to the previous expression is now the lower bound. So since 31802, minimum amount of shear reinforcement is a function of concrete compressive strength. So A sub V minimum is given by this expression, except that it shall never be less than that, irrespective of concrete strength. Okay, this I showed you and described to you already, so there is nothing more. Minimum shear reinforcement shall be provided where, okay, this is another pretty important topic. So theoretically, if V sub U, the required shear strength, is less than phi times V sub C, the shear that concrete alone can carry, you should not need any shear reinforcement, right? If concrete alone can carry all the shear, if V sub U is less than phi times V sub C, then why would you provide shear reinforcement? Now, minimum shear reinforcement shall be provided where V sub U exceeds not phi times V sub C as you would expect, but 0.5 phi times V sub C. Okay. So please note that we provide minimum shear reinforcement as soon as V sub U exceeds 0.5 phi times V sub C, half the shear at which we would normally expect to provide shear reinforcement. Now, there are exceptions to this, except in members satisfying one or more of the following conditions. You do not have to provide shear reinforcement until the V sub U equals P times V sub C in members satisfying one or more of the following conditions. Footings and solid slabs, okay, we do not provide shear reinforcement unless shear exceeds P times P sub C. Hollow core units, so these are members in which no shear reinforcement needs to be provided unless shear is phi times B sub C or more. No shear reinforcement at half of phi times B sub C. Footings and solid slabs, hollow core units with total untopped depth not greater than 315 millimeters, and hollow core units with V sub U is no greater than 0.5 phi V sub CW. Okay, that crept in. Anyway, this list I don't have to dwell on every. So concrete joist construction as defined in 318. No shear reinforcement at phi times B sub C by 2. Beam with total depth not greater than 250 millimeters. Beam integral with slabs with H not greater than 600, not greater than. Anyway, I'll let you read this list. So there are certain things for which we do not need minimum shear reinforcement unless the V sub U exceeds P times V sub C. Experimental tests indicated that some conditions such as deep, lightly reinforced one-way slabs and beams, flexural members with high-strength concrete, and flexural members having concrete with small coarse aggregate size resulted in failure at shear loads less than V sub C, and this is why most of the time we provide shear reinforcement as soon as V sub U exceeds 1/2 of P V sub C. Providing minimum amount of shear reinforcement is a prudent approach for flexural members subjected to repeated loading, even though shear reinforcement is not required based on calculation and or experimental static tests. Minimum shear reinforcement requirements shall be permitted to be waived. This has been in the code for a long time. I would say this is a problematic provision. Anyway, let us read it. So, minimum shear reinforcement requirements shall be permitted to be waived if shown by test that required M sub n and P sub n can be developed when shear reinforcement is omitted. Okay, if you can demonstrate you don't need shear reinforcement, you don't have to provide shear reinforcement. That's what it's saying. Then, such tests shall simulate effects of differential settlement, creep, shrinkage, and temperature change based on a realistic assessment of such effects occurring in service. This is the problematic part. I remember, it has been a while. Anyway, a client came to me. He wanted to get this exemption. And should I come out, observe the test, and certify that the second part has been satisfied. Such tests are simulate effects of differential settlement, creep, shrinkage, temperature change based on realistic assessment of such effects occurring in service. It probably can be done. It's not easy to do, and to satisfy the building official that you have done that is pretty challenging. So yes, this is theoretically a way out. Practically, I do not know how many have succeeded in doing that. When shear reinforcement perpendicular to axis of member is used, so this is now the reinforcement part. Okay, we talked about V sub C quite a bit. V sub S is A sub V F sub YT. that would be shear carried by one piece of shear reinforcement times the number of shear reinforcement crossed by a diagonal crack, which is the D over S part. So V sub S is A sub V F sub YT D over S. Where circular ties, hoops, or spirals are used as shear reinforcement, V sub S shall be computed using the equation that I showed, where D is defined in section such and such for circular members. Remember, 80% of the diameter. A sub V, important. So we are talking about circular ties, hoops, or spirals. A sub V shall be taken as 2 times the area of the bar in a circular tie, hoop, of spiral at a spacing S. S is measured, etc. S and F sub YT, I think, are clearly understood. Then there are expressions for V sub S for this inclined bars and things, which I will skip. I don't know that. Those are of high interest. Okay. Then this may be, even though this is inclined bar, this is I think important. So only the center 3/4 of the inclined portion of the longitudinal bend bar shall be considered effective for shear reinforcement. V sub S shall be computed as the sum of the values computed for the various types of shear reinforcement. This is important. If you have inclined bars and stirrups, the V sub S will be the combined contribution of the inclined bars and the stirrups. Okay. V sub S, the contribution of the reinforcement shall not exceed 8 square root of F sub C prime in our units. 6 square root of F sub C prime. Okay. So that means the sum of the concrete contribution and the steel contribution shall not exceed 10 square root of F sub C prime. Concrete is good for 2 square root of F sub C prime. Steel cannot exceed 8 square root of F sub C prime. So the total nominal strength of a section cannot exceed 10 square root of F sub C prime, 0.83 in your units. Okay. So that is because at a higher shear stress, the shear is transmitted from the point of application down to the ground via compression struts that form in your member. And those compression struts will crash in compression irrespective of how much reinforcement you may or may not provide. So that is why there is an absolute upper bound. Okay. V sub n shall not be any more than 10 square root of F sub C prime. The reinforcement contribution shall not exceed 8 square root of F sub C prime. So phi times V sub n is phi times V sub C plus V sub S has to be larger than or equal to V sub U. That tells you the spacing you need of the shear reinforcement, spacing of shear reinforcement. These things I think are familiar to most. Spacing limits for shear reinforcement placed perpendicular to the axis as long as V sub S is less than or equal to 4 square root of F sub C prime. The maximum spacing is D over 2 or 600 millimeters, 12 inches. Okay, I'm sorry. 600 is 24 inches. Yeah, anyhow. So D over 2 or 600 millimeters.
24 inches.
Say that again.
24 inches.
Yeah, okay. So as long as V sub S is less than or equal to 4 square root of F sub C prime, the maximum spacing is D over 2 or 24 inches. When V sub S is larger than 4 square root of F sub C prime, that goes down to D over 4, but never more than 12 inches. Okay. So maximum spacing. Yeah, this is the incline bar stuff that I am going to skip. Okay, so that was, I will show you an example, numerical example, which will make things fall in place. So I started from strength of materials, as you saw, trying to make the point that we are designing for diagonal tension, and then the concrete contribution to shear strength, the contribution of the shear reinforcement to shear strength. The concrete contribution has multiple parts: the shear in the compression concrete, the dowel shear, the aggregate interlock shear, and all of that we kind of lump together in typical applications. Anyway, then for design purposes, minimum reinforcement, the maximum spacing. So we have covered everything that will enable us to solve real life problems, and we will do one or two of them. Deep beams is a topic that used to be covered in at length in SEI 318 up to the 99 edition. Then much of it was thrown out. I suppose the logic was this is now textbook material, and what is left is very little. But anyway, let me take you through. I think this is a fairly important topic, and again, I would like to show you an example. So deep beams, by definition, these definitions keep on changing. So remember, your code is 31808 BNBC 2020. Okay. So everything I tell you is 31808 BNBC 2020, unless I specifically mention this is how it was in 31899 or something like that. Okay. So these definitions are 31808 BNBC 2020 definitions. Deep beam has clear span less than or equal to 4 times the overall depth of the member. Okay. Less than or equal to 4. So span to depth ratio is 4 or less. Clear span to total depth ratio is 4 or less. Or it could be portion of a beam where concentrated loads within twice the member depth from there is a concentrated load within twice the member depth, loaded on one face, supported on the other face, so that compression strut can develop between the load and the support. So imagine a portion of a beam, let us say the left end is on a support. At some distance away from the support, a concentrated load is applied on the opposite face within twice the member depth from the support face. This portion of the beam is also a deep beam. Deep beams shall be designed using either nonlinear analysis as permitted in section such and such, or Appendix A, which is strut and tie model. So that's about all 31808 tells you. Nonlinear analysis, because if it is a deep beam, plane sections don't remain plane anymore. Now, in addition to that, all we are told is the nominal shear strength as per a regular beam shall not exceed 10 square root of F sub C prime. Very importantly, 31808 tells you a reference may be made to 31899 for detailed design procedures. So we took it out of the code, but it is still good to use. 31808 tells you that. And then this is very important. So in a deep beam, you have to have not only vertical shear reinforcement as in a conventional beam, but also horizontal shear reinforcement. Shear reinforcement perpendicular to the flexural tension reinforcement. Minimum amount, this is the vertical steel, is 0025 B sub WS, so one quarter of a percent. Maximum spacing is D over 5 or 300 millimeters. So these are the minimum on the vertical shear reinforcement perpendicular to the flexural tension reinforcement. The horizontal shear reinforcement parallel to the flexural tension reinforcement. Minimum is 0.15% and the maximum spacing is D over 5 or 300 millimeters. These I have taken from 318.08, not 318.99. Okay, so these are your numbers. And then I will show you an example, and then hopefully things will fall in place. Okay, it's a few minutes to 10. I don't know, I kind of hesitate to. I have 3. So Bodhi, a break, or let's take exactly 5 minutes, okay?
There was a few people asked for break, but I told them that only that you have a lot of content to cover.
Let's take just 5 minutes before I start on the examples. So 2 minutes after the hour, we'll get back. 2 minutes after 10. Okay. Okay, it's 2 minutes after 10. I'll start. I truly admire you. I was thinking 5 days a week, Saturday, Sunday, Monday, Tuesday, Wednesday of training for 3 hours, 4 out of the 5 days after work. This is an awful lot, and we had no choice. We had to compress the schedule to have the exam before Eid. At the same time, I totally, completely understand it is tough on you. So the best we can do, I think, is to make the lectures clear, and hopefully these examples help in that regard. Okay. Yeah. And anyhow, stick with us. I think you will benefit. There is no question in my mind. So it's all worth it. Okay. So it's, as you see, a beam with uniform loading on it. The beam is supported on columns at the two faces. 6 meter clear span. The section is 400 by 550. Concrete strength 40 MPa, F sub Y 420. Okay. Here it doesn't talk about how much reinforcement. At the face of the support, the shear is 115 the units are 115 kilonewton per meter uniform load, multiplied by the clear span of 6 divided by 2, that's 345 kilonewton. Critical section for shear is a distance d away from the support face. D is 550 millimeters. So V sub U is the 345 at the support face minus the 115 kilonewton per meter load multiplied by the 550 millimeter, which is 5 meter. So that gives us 282 kilonewtons of shear at the critical section as opposed to 345 at the support. Sections located less than a distance d from the face of support may normally be designed. We have gone through all of that. Okay. So we have a shear, design shear of 282 kilonewtons. How much can concrete carry? 0.17 square root of F sub C prime B sub W D. So 0.17 square root of 40, B sub W is 400, D is 550. That is 236 kilonewton. 282 is what we want to carry, 236 well, this is the nominal. For phi is 0.75, so the 236 gets down to 177 kilonewton. So we have 282 kilonewtons of shear to carry. Concrete can carry 177. The rest has to be done by reinforcement. Now here we are figuring something. You don't have to do it this way, but this is a fairly good way to do it. Distance from the support face to where V sub U becomes equal to phi times V sub C, 177 kilonewton. So beyond that, at least theoretically, we do not need any shear reinforcement. Okay, that distance comes out to 1.5 meters. And then we find the distance from the support face where V sub U becomes 1/2 of phi times V sub C, which is 88.5 kilonewtons. And that distance comes out to 2.2 meters. So V sub N 282 kilonewtons at D from the support face. the shear gets down to phi times v sub c at 1.5 meters from the support face. So beyond this point, theoretically, we do not need shear reinforcement, but practically we do, because you remember we cannot drop shear reinforcement unless shear drops below phi times v sub c by 2. That happens at 2.2 meters from the support face. Okay, so now we have our entire picture. So shear reinforcement needs to be designed for the length of the beam from each support face up to 1.5 meters from the supports. Minimum shear reinforcement needs to be provided between 1.5 meters and 2.2 meters from each support face. Beyond that, we don't even need the minimum. So V sub u minus P times V sub C in our case is 345 minus 177 is 168 kilonewtons. And that is less than 0.66 phi square root of f sub c prime. So if we go for 12 two-legged stirrups, two legs have a total cross-sectional area of 226 square meters. The spacing comes out to 233 millimeters from this expression. Okay, 233 millimeters. So 233 is the required spacing. What is the maximum permissible spacing? Our shear is lower than 4 square root of f sub c prime. So our maximum spacing is 1/2 of d, or 600 millimeters. 1/2 of d is 275 millimeters. Remember, d is 550. And that is larger than the number we calculated, 233 millimeters. So this number is smaller than the maximum spacing, so we can go with that number. So we will provide 12 two-legged stirrups at 230 millimeter spacing. And then calculate minimum shear reinforcement. Remember, the minimum, the concrete dependent minimum is 86 square millimeters. The absolute minimum is 77 square millimeters. We are providing 226. Obviously, we are way above the minimum in this particular case. Okay. So up to 1.5 meters from the support face, we have provided this 220 or 320 millimeter spacing. 230. Okay. Now, between 1.5 meters and 2.2 meters from the face of the support, minimum shear reinforcement needs to be provided. So what is the spacing of minimum shear reinforcement? It comes out to, we know how much the minimum shear reinforcement is. This is the concrete dependent minimum. This is the absolute minimum. So the spacing of the minimum shear reinforcement is 605 millimeters, and the spacing of the absolute minimum shear reinforcement is 678 millimeters. We cannot provide those. the maximum spacing is 275. Remember, 1/2 of d is the governing. So even beyond 1.5 meters, we will provide two-leg stirrups at 275 millimeter spacing. That is the largest. So place the first stirrup at 120 millimeters from each support. This from should be at, and anyway, place the first stirrup at 120 millimeters from each support. Place 6 stirrups at 230 millimeter spacing, starting from 350 millimeter from each support and up to 1500 millimeter from each support. Okay, get that? So the first one is 120, then at every 230 up to 1.5 meters. And beyond 1.5 meters, place 10 stirrups at equal spacing, which is 273 millimeters. We said 275 is the maximum, and that will cover the entire span of the beam. So if you just read the example once or twice, you will see that it's pretty simple stuff. So the first one at 120, then a few at the 230, and then the remainder of the beam span is covered by the same reinforcement at a spacing of 273 millimeters. And this is the complete design, shear design of the beam. Okay, let's do a deep beam for shear. This you will not find too many places, so I think you may. I think you will probably like it and it may be useful to you. So 1500 by 500 is the section. This is a deep beam. Well, we'll figure out whether it's a deep beam or not. This is the load applied at the 0.5 meter is the width of the column or whatever. This is a transfer girder. This is a column coming down and then on the girder, and then the girder is supported on two columns that are 3.6 meters apart, and the columns are 0.4 meters, 400 millimeters wide. So this is 1.8 meters, this is 1.8 meters. 1500 by 500 is the section. F sub C prime, F sub Y, dead load from the column is 800 kilonewtons, and live load from the column is 1100 kilonewtons. Okay, those are what we are dealing with. So on the transfer girder, the column transfers 800 kilonewtons of dead load and 1100 kilonewtons of live load. The dead load of transfer girder, the transfer girder itself has a weight. It has a section of 1500 by 500. So the weight of the transfer girder is lumped with the column load at midspan. Okay, we will just assume that the dead load of the transfer girder also acts at midspan as opposed to being uniformly distributed. So the dead load of the girder is, remember, 500 by 1500 section. 3.6 is the span. 2400 kilograms per meter cubed is the weight of the concrete, the mass rather. You have to multiply that by G to get it into kilonewtons. This is in meters per second. And so that is the total weight of the transfer girder in kilonewtons, plus 800 is coming from the column, for a total dead load of 864 kilonewtons. So the load combinations, we have only two. 1.4 dead is that much, or 1.2 dead and 1.6 live being 1100 kilonewtons. That gives us 2797. That is obviously the governing load case. Okay. Something happened. Something changed, Bodhi.
Can you try pressing escape? Pressing escape from your keyboard.
Yeah. Okay. It is still large size, right? Yeah, okay.
Yep. So
So,
it is big.
so the governing load is 2797 kilonewtons. So we are showing the 2797 at midspan, and that will give us support reactions of 1399. So clear span 3.6 feet, overall height of beam is 1.5 meters. Clear span to total depth ratio is 2.4. That being marked, that is obviously less than 4.0. The beam is loaded on one face, supported on the opposite face. So this is definitely a deep beam by the definition of ACI 31808. ACI 31808 requires analysis accounting for nonlinear strain distribution or use of start and time model for deep beam design. In this example, the deep beam provisions included in section 11.8 of 31899 are used to account for nonlinear strain distribution in the beam. Okay, so this is what I basically wanted to show you, the way we typically have done it. So, assuming effective depth D of 90% of the total depth of that, so D then comes to 1350 millimeters. That is an assumption, but not a bad assumption. Distance from critical section for shear from support face is, so this is in 31899. Distance of critical section for shear from support face is 50% of the distance from the support face to the load, and that is 900 millimeters. That being less than D, 1350 millimeter, that is where the critical section is. Because the shear distribution is, now here it doesn't matter because the shear is the same. It's one concentrated load in the middle. So from the support to the load, it's the same shear. Because the shear distribution is uniform from the support to midspan, the shear demand does not change from the support face to the critical section. So V sub U at the critical section is also 1399 kilonewton. V sub C is given by the same expression as before, 2 square root of F sub C prime. That comes to 726 kilonewtons. Reduced by phi, that gives us 545. Obviously, 545 is less than the 1399 that we need to resist. Thus, shear reinforcement needs to be provided. Now, this is the 31899 expression for the V sub S, the contribution of shear reinforcement. Okay, so remember we have vertical shear reinforcement and horizontal shear reinforcement in a deep beam. The vertical is S sub V. The horizontal is S sub VH. S is the spacing of the vertical reinforcement. S sub 2 is the spacing of the horizontal reinforcement. Okay. So the area of shear reinforcement perpendicular to flexural tension, A sub V, shall not be, I have taken you through all of that. So the vertical shear reinforcement minimum is 0.25%. Maximum spacing is 1/5 of D or 300 millimeters. Whichever is less. The horizontal shear reinforcement minimum 0.15%. The spacing is D over 5 or 300 millimeters, whichever is less. Okay. So minimum reinforcement ratio. So minimum horizontal reinforcement ratio is 0015. Try two number 16 millimeter diameter bars. That will give us A sub VH of 402 millimeters. So required spacing would be 536 millimeters. If we want 0.0015% reinforcement using two numbers 16, like one number 16 on each face. That's what it means. Then the spacing of the horizontal shear reinforcement is going to be 536 millimeters. That is too much. The maximum allowable spacing is 1/5 of D, which is 270 or 300 millimeters. So it is actually 270 that governs. So as far as horizontal reinforcement goes, we will provide number 16 bars, two number 16 at 270 millimeters. Okay, two number 16 at 270 millimeters. That is horizontal shear reinforcement. V sub S will be V sub U by phi minus V sub C. And that is given by, you have seen the expression for V sub S. Okay, so using two-legged number 16 stirrups, A sub V would be 402 square millimeters. So in this entire expression, everything is known other than the S. Okay, that's the only unknown. Everything else we have, you know, once we have decided that we are going for A sub V of 402 millimeters in this entire expression, only unknown is the spacing of the vertical reinforcement S. When you solve that equation, S comes out to 126 millimeters. And so we are saying provide two-legged number 16 stirrups at 120 millimeters as vertical shear reinforcement. That will give us a percentage of 0067, which is larger than 0025 minimum that is needed, so that's okay. Maximum allowable spacing is 270, so 120 is totally fine. So we have decided on the vertical and the horizontal shear reinforcement. Now we will make a final check. V sub S from this expression comes to 1167 kilonewtons for the exact vertical and horizontal reinforcement we have provided. So V sub N comes out to 726 concrete contribution, 1167 reinforcement contribution, total of 1893 multiplied by a phi, it comes to 1420 kilonewtons, which is larger than the 1399 that we need. So the shear does not exceed 10 square root of F sub C prime, so we are okay on all counts. So this is a complete design of a deep beam. As I said, you will not find it all that commonly anymore. This was last time in 31899, so I thought that I would show it to you. Then shear design of a one-way slab. I have 5 minutes of regulation time. It should be okay. I may go over by a couple. So we have seen this in the flexural design calculation. There are several supports, not just one. This is the one-way slab spanning from left to right, and we take 1 meter width of the slab as a beam to design the slab. Okay. The clear span is 7 meters. Concrete strength, steel strength, superimposed dead load is 2 kilonewton per square meter, live load 2.5 kilonewton per square meter, slab thickness is 305, effective depth is 305 minus 20, clear cover 16/2, half the diameter of the reinforcement that we are using in the slab. That comes to 277 millimeters. Self weight of the slab 305 millimeters, 2400 kilograms per cubic meters. 981 is the G. That gives us 7.2 kilonewton per square meter. Total dead load then is 7.2 plus the superimposed 2 kilonewton per square meter, that's 9.2. So the load cases, 1.4 dead load is 1288 kilonewton per square meter, 1.2 dead plus 1.6 live comes to 15.04 kilonewton per square meter. So that is the governing case. Now we want to find the shear at the support by using empirical expressions that are in ACI 318 section 833. In order to be able to use those, there are some preconditions to be met, and here we are saying that all the preconditions are met. You can read those. Okay. So based on an end span and a strip width of 1 meter, shear in end members at face of first interior support is 1.15 W L sub n over 2. 1.15 W sub U L sub n over 2. That's the shear in end members at face of first interior support. So that's 60.5 kilonewtons. Shear at faces of all other supports, it is just W U L sub n over 2. So going back, if this is the first support and there are many supports afterwards, the highest shear will be at the interior face of the first at the exterior face of the first interior support here, and that would be 1.15 WLN over 2. And then at all other supports, it will be simply WL sub n over 2. So the highest is 60.5 and at the other supports 52.6. So at the face of the support, the 60.5, the highest value. Critical section for shear is at a distance D from the face of the support. D, we calculated, is 277. So the 60.5 kilonewtons of shear goes down to 56.3 at the critical section. 56.3. Out of that, V sub C is 297.8. So we have 56.3 kips of shear at the critical section. Concrete alone can carry 297.8 times 0.75, which is 223.4. Obviously way larger than 56.3. So here we do not need any shear reinforcement. This is very typical of slabs. It's seldom, if ever, we will need shear reinforcement for one-way shear. Minimum shear reinforcement is required when V sub U exceeds 0.5 P V sub C. However, this requirement is not applicable, remember, for solid slabs. So our design is done. We do not need any shear reinforcement. Okay, so I'm 1 minute late. That's not bad. So I'm open for questions for the next half hour. And we will do probably the same way. So you are going to read to me?
Yes, Dr. Ghosh. So there are a lot of questions, but many of them I answered during the webinar.
Okay.
And Dr. Rakib is also there. So
Okay, good.
I made him a co-host. So if he can pretend to.
Okay.
Yes, some points. Okay, so I will start. Okay, this is just a comment. Mhm. Is horizontal shear reinforcement
Mm,
mandatory for all deep beams,
mm.
or it is just needed when required?
Horizontal shear reinforcement is mandatory for all deep beams, yes. And even when you do not have a deep beam, by the definition of deep beam, we have something called skin reinforcement. When I forget where it's, I I think it came up when I was doing the flexural module. Remember skin reinforcement? I think that starts at beams exceeding 900 millimeters in depth. Don't quote me, check it out. But even when you don't have a deep beam by the definition in SEI 318, you have a beam that has a depth of, I believe, more than 900 millimeters. You need skin reinforcement. So, but the horizontal shear reinforcement in a deep beam is mandatory. Yes.
Yeah, Dr. Ghosh, you are right. It is 900 mm. And,
Okay.
that thing is also mentioned in BNBC 9.5.3.2. So I'm just giving you extra information. Um, okay. Why the first reinforcement of beam use 50 mm from the support?
Say that again.
It's I'm just framing the question back. Um, why is the first shear reinforcement for a beam uses is at 50 mm from the support?
I don't know if 50 is a
I think it's
requirement, but
yeah.
we we you need to place it. Yeah, 2 inches is what we do. I don't know that it's a requirement. It's a sensible sensible short distance away from the support face.
Because isn't 2 inch a requirement for special moment frames that you have to have a reinforcement within 2 inches?
I don't believe. I don't know without checking, but I don't believe so. We Yeah, it's just a, as I said, a sensible small spacing.
Okay,
If it is a requirement, it may be, but yeah, without checking, I don't know.
okay. Which gives a better load transfer mechanism? One-way slab or two-way slab?
That question is, I don't know what to. You don't get to choose, okay? So it all depends upon uh, how do I want to say it. The first thing is, do you have beams or don't you have beams? If a slab is supported directly on columns and there are no column line beams, they are two-way slabs. Nothing you can do about it. Okay, the and a flat plate, as we call it, a slab supported directly on columns. A flat plate transfers 100% of the load applied on the slab in each orthogonal direction. That's discussion for another day, and that day will come, I think, in a week or so. Anyway, so but if you have beam supported slabs, then the load is transmitted. Load applied on the slab is transmitted to the supports by bending in both directions, in the short direction, in the long direction. Short direction bending transmits more of the load than the long direction bending. The short direction is stiff, the long direction is flexible. The stiffer direction transfers more load. And so by the time you are looking at a long to short dimension ratio of 2 or more of your slab panel, you have a slab supported on beams on all four sides, presumably rectangular slab. If the long side to the short side of this rectangle becomes 2 or more, then bending in the long direction transmits very little load. It is the bending in the short direction that counts. Then we call it a one-way slab. Okay, that's all there is to it. There is no one-way slab that is not beam supported, cannot exist. All slabs without beams are two-way slabs. If you have beam supported slabs, whether it's one way or two way, will depend on the dimensions of the slab panel. Is probably the best way to say it. Okay.
Okay, Dr. Ghosh. So are deep beams or transfer girders safe for earthquake zones, especially in severe zone or moderate zone like in Bangladesh?
That is a very good question. Well, we have strong column weak beam requirement by which you cannot really have deep beams. At the same time, I hesitate to say that transfer girders are not are prohibited. I wouldn't go that far. I how should I say? you have to be doubly careful in designing those transfer girders in seismic areas. You transfer girders, if you prohibit transfer girders, you are uh, you are restricting the architecture of buildings to an extent that is really not warranted. I think we should be able to, we are able to do them. So no, I wouldn't go so far as to say they are prohibited. However, they're more challenging in high seismic applications.
Yes, Dr. Ghosh. So you answered two more questions which were kind of related. Okay. When combined shear and torsion can be released, that is not considered in the design of beam.
Read that one more time, please.
When should we not consider combined shear and torsion in the design of beam?
I will fit torsion in somehow and go into that. There is something called threshold torsion below which torsion doesn't have to be considered. Otherwise you have to. Shear is pretty much always there. And if torsion has to be considered, then it is combined shear and torsion. So there is something called threshold torsion below which we do not have to consider torsion.
Okay, so you answered two more questions because they were related, so you kind of answered that. So. If web shear crack develops in a beam, would FRP warping, I think wrapping, increase its shear capacity? Fiber reinforced polymer, basically. That's what is.
Yeah, the wrapping, I have never seen wrapping used in new construction to boost shear capacity or anything else. Wrapping is almost exclusively and a retrofit measure after something has happened to restore shear capacity and so forth, wrapping is quite effective. Now, something that is being, you would say, tried or has been actually used, and ACI 318, not in '08, but in recent times has allowed qualified usage of that, is steel fibers in concrete. That does improve shear resistance, and that is a promising avenue that is being pursued now more and more. Other types of fibers have different problems. The carbon fibers, the synthetic fibers, but steel fibers have proven to be a good way to go in some applications. So that's where I would leave it. It is not common to use that in members that are prone to web shear cracking. Not common at all. But if you're looking for something to try, it will not be wrap. It will be the fibers in the concrete mixture.
Thank you, Dr. Ghosh. So is it okay to provide stirrups in closed spacing to confine the concrete, even if the shear requirement is not that much?
That is we do that all the time. If you are in a high seismic application, the confinement requirements are so high that we end up providing. In that case, it is not stirrup. It has to be closed transverse reinforcement called hoops. You take a column in design category D, which will be the newer parts of Dhaka. You go to Uttara or wherever near the airport. So design category D column, the confinement requirements are so high that the hoops that you will provide at tight spacing, those will be way more than what is needed for shear, way more. Yeah, this is common. This is all the time.
Okay.
Dr. Rakib, you are free to step in if I am saying something there.
Thank you, sir. Sure, I'll do if I think.
Thanks. I haven't said something that's not so far, right?
No, it was absolutely okay.
Okay. So what is the minimum shear reinforcement diameter that we try to meet? I don't understand what.
Maximum shear reinforcement, minimum shear reinforcement diameter is number 3, which is what? 75 by 8. So number 9 millimeter. Yeah, 9 or 10. Yeah, that would be the minimum.
Okay. So provisions for the placement of torsion rebar.
Say that again.
Provisions for the placement of torsional rebar.
We haven't discussed torsion. Let's wait.
Something for.
Let's wait. Yeah, torsion is different. It requires close reinforcement. We haven't gone there yet.
So coupling beam design requires diagonal shear rebars when the shear exceeds 4 roots of Frank C. Can this diagonal rebar be utilized as flexural rebar as well?
Yes.
The diagonal shear rebar, horizontal and vertical shear rebar, and flexure rebar all together create such congestion that concrete pouring becomes difficult.
Read that last sentence again.
The diagonal shear rebar, horizontal and vertical shear rebar, and the flexure rebar all together create such a congestion
Yes.
that concrete pouring becomes difficult.
Yes. I agree. So you have to be you have to be very mindful at the design stage. This is true in that situation. This is true in all situations, particularly high seismic design. You have to remember that ultimately, this is the, how should I say, the irony of the situation. So if you look, you would conclude that, well, obviously, concrete cracks doesn't carry any tension. It needs reinforcement to do almost anything for you. The reinforcement is absolutely vital. Okay? But then most people don't stop to think that the reinforcement doesn't do much for you either unless it is encased in concrete. The concrete is absolutely essential. Without concrete, the reinforcement is not going to carry loads for you. So do not forget that the concrete has to get in. So the best thing to do is to draw all the reinforcement to scale at the design office before construction has started, and make sure that concrete of the aggregate size that you are planning to use with normal admixtures, not these super admixtures which are very expensive, will pass through the gaps that you have provided. Otherwise, there will be trouble. There will be calls from the job site, and all the solutions will cost you money. So what you say is absolutely correct. It's a very congested situation that you are dealing with in a diagonally reinforced coupling beam. That is one problem. The other problem is that the diagonals will have to be bent into the walls at the two ends, and to develop those beams you need quite a bit of room. That room quite often is not available. So there are problems associated with well, many things we do, there are problems associated with them. So that the thing is to be aware of them, and secondly, to, as I said, to do the right thing. You have to make sure that the concrete will get into place before construction starts. At the design office, you have to make sure. Otherwise, there will be problems.
How should we consider? Just a second. How should we consider the effect of any openings in beam members? There. So
there is no one answer to that question. Depends entirely on how large the opening is. So this is why, instead of going into that paper by George Barney, one of the four, take a look at that. I think there is quite a bit of good stuff in that paper. It's not one solution. If it's a tiny opening, it may not mean anything. If it is a little bit larger than that, we will just put rebars around. But then you want to pass HVAC ducts through a beam. It's a problem that you will have to deal with. So no, there is no one answer to that question.
Okay, Dr. Ghosh. Can we use 8 mm bar as stirrups? Does BNBC 2020 allow that?
8 millimeter as stirrups. Dr. Raki would know. I don't believe there is a prohibition, but something that thin. Those thinner bars cost more, at least in the US. I don't know in Bangladesh. And yeah, I don't know. I'm not aware of any prohibition unless Dr. Rakib can tell us. But 8 millimeters is very thin. I don't know if you have seen those. Those are very thin bars. And
Dr. Rakib, do you want to pitch in that?
There is no prohibition, as Dr. Ghosh said, and 8 millimeter bars are not very common.
yeah,
They're used, but they're not very common. And I don't know about the cost, but you're right that for lesser dia bars, more work has to be done at the manufacturing site. So it may be a little bit more costly.
Yeah, typically here number 3s cost more than the 9 millimeter. They cost a bit more. 8 millimeter is not manufactured here. There was a long time ago a number 2, which is a quarter inch, 6 millimeters. That was a long time ago. That has been gone since the 60s.
Right.
Okay, what else?
Again, yeah, few questions are about detailing in seismic design category D, but I think that you will cover in the later lectures. So
B, I don't know how much I will cover. C and D I will cover in.
no, D only, D. That's what I'm saying.
D, yeah.
So
Sure.
that will be covered in depth basically afterwards.
Sure.
So I don't think we should get into that right now.
No.
How should we consider a shear rebar in an arch beam?
Shear rebar in an arch beam. Arch beam, I don't know. Arch beam, you don't need shear rebar, do you? It's arch is compression. So the whole idea is that you are carrying loads in compression. There may be a tie between the ends, which will be the tension member. I don't think there is any shear involved if it is a real arch. Like in a truss, there is no shear. Shear is a bending thing. Shear is caused by bending.
Right.
Arch is compression.
Can we use, just a second, let me frame this question. So is there any restrictions to incline stirrups for any beam or any kind of requirements?
I don't know of any restriction except BNBC says more than 45 degrees. So look at that. You know, that's the only thing I read. I do not know. Inclined stirrups are not common. I personally have not dealt with them. I don't have any feel for them. But the only restriction I have seen is this, more than 45 degrees.
Okay, just going through the questions. So near support of columns, sometimes the stirrups are bigger with respect to longitudinal rebar of beams due to placement of column rebars.
No, you have to say it again.
Yeah, these questions I have to it's hard to read it like that because it has to be framed properly. So near the support of columns, Sometimes the stirrups are bigger with respect to longitudinal rebar of beam due to placement of column rebar. Could you please tell me how to solve it in practical field? So bigger, does he mean by bigger diameter or?
I
think
don't know.
Yeah, this question is not clear.
I was listening pretty closely. I do not understand. So try to read it one more time.
So near the support of columns, sometimes the stirrups are bigger with respect to longitudinal rebar of beam due to placement of column rebar. Could you please tell me how to solve it in practical?
No, I don't know what that means.
Yeah,
What he's trying to ask.
and even I am confused.
Okay, see everybody tomorrow again. Same hours.
Thank you.
Okay, thanks a lot, buddy, for everything you do. Thank you.